Hello everyone, welcome to Chip Confessions. In our design verification course, this is the fourth session and we shall see what are all we are going to learn in this session. So, we are learning about HDLs, means what is HDL and some examples of HDLs, and then why HDLs are important, then HDL versus any of the software programming languages, and then the comparison between Verilog and VHDL, which are both are the types of HDLs only, and then we will see how we can execute using, means what are the online or offline simulators we can use for executing Verilog code. So what is HDL? HDL stands for Hardware Description Language. Means in our first video itself we saw what is hardware description language. Means whichever the language or the programming language we use to describe any digital circuit or a system, that is called as hardware description language. So any circuit we have, if we are writing the same circuit in terms of code, then it is called as hardware description language. And then the examples of HDLs are Verilog, which is widely used for designing as well as verifying some digital circuits. In the previous years we were having mainly Verilog, means we didn't have system Verilog or UVM as of now. Mainly we relied on Verilog for even verifying the test benches also. Later on, with few enhancements, we got system Verilog and OVM and other verification methodology languages also. The thing is, mainly Verilog was used for design and verification both, but now we are relying Verilog more for designing only, and for basic testing and basic test benches we use Verilog. And then VHDL, which stands for VHSIC Hardware Description Language, that is Very High Speed Integrated Circuit Hardware Description Language. It is also one of the types of HDL which is mainly used for both mainly used to write both RTL design and verifying the design also. But the usage of VHDL is like in aerospace or defense or FPGA projects only, means it is not widely used as Verilog. We shall see the difference between Verilog and VHDL in further slides. And then is System Verilog. System Verilog is just an enhancement for Verilog, and it has got few extra design concepts also that we will see when we start with System Verilog. And then is System C. System C is a language which is based on C++ libraries, and it is mainly used for high level modeling and system architecture exploring. The thing is, in System C we can't synthesize as we do in Verilog, means we cannot convert into circuit level or the gate level, that we can't do. But what we can do is for high level modeling, means like system level designing, that we can do with System C. Like hardware proper synthesizing, if we can do with Verilog and VHDL or System Verilog, this we can do for like, means parallelly we can do in System C at a very high level, means this is not used for synthesis. So HDL stands for Hardware Description Language, and the examples are Verilog, VHDL, System Verilog and System C. Whereas Verilog is widely used in the industry and VHDL is used but still restricted among the domains such as aerospace, defense and FPGA projects. And then is a System Verilog. Nowadays System Verilog also is getting popularized because of its enhancements from Verilog, and the System C is mainly used for high level modeling rather than synthesis. Next we shall see why HDL. Means we have got lot of programming languages. We know C, we know C++, we have Python, we have Perl, we have Java, we have Ruby, what not. We have like hundreds of programming languages we have. But why hardware description language? Why can't those languages? Why can't we do anything with those software programming languages? Let us see those reasons why HDL is important. One is scalability. What is scalability? Means whenever we are creating a design which is very large, at that time we can't do everything by hand. In the initial days, what people were doing, what engineers were doing, they were drawing schematics with their hand. Each gate they were drawing and each gate they were connecting with their hand. But later on, when the complexity started increasing, we have to rely on something which can do this on our behalf. Means on the engineer's behalf, some software or some language should be there which can convert whatever we write into the schematics. Then came this HDL. And scalability is nothing but whenever the design is getting more complex, at that time it should be able to adapt itself. When it is just single AND gate, the way it performs, the same way it should perform when we have like thousands of AND gates. This is how is scalability. So these HDLs are required to ensure this scalability. And then is the reusability. What is reusability? Means whenever we are using a HDL modules and we write in terms of modules, means whatever the design is there, that we write in terms of the modules, and that can be reused with different designs. For example, we have half adder. You know, in digital electronics we have half adder, and using that half adder we can make a full adder, and using that full adders we can make ripple carry adder, like that. Or 2x1 mux we have, using that we can make further higher order mux. Or decoders we have, we can make higher order decoders. Encoders we can make higher order encoders, like that. That reusability will be there. That is what it is. Like, we are making a smaller design and we are using the same thing for higher level designs. That is what reusability is. We are using the same design to build something higher. Then we have simulation and verification. This is one of the major advantage. What happens here is that functional simulation can happen before the actual hardware is built. Like, we are not heading towards like chip fabrication. As we saw in ASIC design flow in our previous videos, initially we do coding, then we just convert them into gate level, or we convert them to a circuit, then we will verify it, and then after crossing so many levels, then we are going for chip fabrication. Means we are simulating it, means we are simulating the design, we are synthesizing the design, we are verifying the design, and later on we are going towards the fabrication, and directly we are not heading towards it. So HDL plays a very important role because it offers us to do the simulation and verification before we get tangible form, like means hardware or the chip we can touch with our hand. Means that before getting physical chip, simulation and verification can be possible because of this HDLs. Next is the synthesis. As I said earlier, synthesis means it is automatically converting, means this HDL is automatically converting that language or that code, whatever we have written, into the gate level circuits, instead of writing everything in hand. Because of these codes, because of this synthesis, we can directly convert that code into circuit level. We need not to sit and write everything by hand. And then is the portability. Means this HDL, as we have a common language, it can be used. For example, you are using in Model Sim, same code. You are using in QuestaSim, same code. You are using somewhere in Vivado, same code. Means the language is common, the syntax is common, and maybe few changes if we have to make according to the simulator, very minimal changes we have to make, but still the same design stands or holds good. That is what portability is. Means this code can be moved across different tools and technologies with no or less or very minimal changes. So these are the advantages or why we need HDLs. One is the scalability, then reusability, and advantages of simulation and verification before the fabrication of actual physical chip. Then we have synthesis, and then we have portability. Next we shall see the difference between HDL and any software programming language. Here software programming language means, as I said before, either C or C++ or Python or Java or Ruby or Perl or anything, any of the common software programming language. So we shall see the differences, means in what feature these two things are different. First is the execution. What happens in execution? In execution, HDL describes the actual hardware behavior where everything runs in parallel. For example, if I say we have AND gate. If we have AND gate, we are giving here we are giving input A, and here we are giving input B, and we are taking output Y. If we have to execute this in any of the HDLs or hardware description language, what happens? You are giving value to input A, you are giving value to input B, and you are taking value of output Y. How we are giving? We are giving A at 10 seconds, B at 20 seconds. Are we doing like that? No. We are giving A and B simultaneously, that is at a time. We are giving inputs for A and B, and we are taking the output Y. The main feature of this hardware description language or HDL is everything runs in parallel. This is the most important feature of HDL. But what happens in software language? In any of the software language like C or Python, everything happens sequentially. Means first line we will be executing, second line it will be executing, and then third line, and then fourth line. That parallel concept is not there in any of the software languages, but in HDL this concurrency or parallel execution is there, which is very much required to give inputs or to take outputs from the gates. Means we are giving clock, for example, and we have thousands or millions of flip-flops. Everywhere clock should go at a time. If clock is going one flip-flop at a time, one flip-flop once, second flip-flop next flip-flop next, like that if it is going, will it create any sense? No, right? For that, execution, that is the parallel execution, is very much important, which can be achieved with HDL only. Next what we have is timing behavior. Here sometimes we use delays in HDLs using, right, for test bench. Whenever we are creating a test bench, we are giving some delays, or we are working like at passage of the clock we are giving, like we are giving timing controls, we are giving delays, which can be achieved in HDL. It is not like it is impossible in software programming language. No, it's not like that, but modeling of the temporal or timing behavior is way more easier in HDL when compared to any other software languages. Then is the concurrency. As I told you before in execution, concurrency is one of the most important feature of HDL, because whenever we are like, we have, for example, say we have initial block. This is one of the procedural block we will be seeing further. This initial block, all the initial block in the code, if we have a code, no matter thousands of initial block it has, everything will run parallelly. So this concurrency is very much important, which can be achieved only in HDLs and not in software programming languages. Then we have the purpose, means why we are using HDL. We are using HDL to model digital circuits or digital system, where Software programming languages are majorly used to perform any calculation or building any database like that. Such kind of application, any database building or some HMI interface or any like GUI interface, building a database, building a stack, for such kind of things we use software languages, whereas HDLs are majorly used for modeling digital circuits or digital systems. Example of this HDL, as we saw, it is Verilog, VHDL, System Verilog or System C, as we saw in the previous slides. And software programming languages examples are C, C++, Python, Java, Ruby, Perl, R, whatnot. Except this HDLs, all are software programming languages only. Okay, then we are seeing the difference between Verilog and VHDL. As we said, Verilog is like majorly like 70% we use Verilog only because ASICs are more, and even FPGA also we can program with Verilog. VHDLs are preferred for Verilog, but VHDLs are preferred for FPGAs, but still even Verilog also can be used to program FPGA. So we can say Verilog is like widely used when compared to VHDL. VHDL, it has restricted application with aerospace or military applications. For such kind of things we use VHDL. Let us see the differences. First one is the syntax. Means Verilog has a very simple syntax, and that simple syntax means like it is, I can say we can compare it with C programming language. And that C programming language, it is simple, as you have seen. You might have studied in your engineering time that C programming language. Verilog has syntax like 70% same, except that flower brackets and all what we use in C. Here we use begin and end. Apart from that, that semicolon and all whatever we use, that and all is way more similar to C programming language. Whereas VHDL uses ADA like syntax. ADA is one of the programming languages. It is a high level programming language which was designed for military applications from US Defense Department during 1970s or 80s, like that, as I remember. Like, means syntax is bit difficult in VHDL, whereas Verilog has a easier syntax. That's what you can remember, like C type syntax and then easier syntax, whereas VHDL has little bit complex syntax and based on ADA language. Then the level of difficulty in learning. The level of difficulty, as I say, Verilog is simpler and easier when compared to VHDL, whereas VHDL is strongly typed language. Like the syntax you have to, it's like when we were learning, we had VHDL in our engineering. Actually we didn't have Verilog, but it was like really initially we struggled a lot. Like you have to remember like proper English kind of things will be there. Let us see the coding examples you will see. Means VHDL has such a kind of like, you will be like, you feel like you will be reading code in English, like you are reading some sentence, like that you will feel when you read VHDL code. But Verilog is not like that. Verilog is very simple, straight. VHDL is not that simple, not that straight also. Means the level of difficulty in learning for beginners, for Verilog it is very less, I can say, and for VHDL it is little bit more. You have to remember lot of things when you are a beginner and learning VHDL. Means it's not like VHDL is impossible. No, it's not like that. Only thing is little bit you have to struggle in remembering the syntax. That's it. Then is the typing structures. As I said, Verilog is loosely typed or like weakly typed, whereas VHDL is strongly typed. Everything will be like proper English words. We will see. I don't know, I'm excited to show you VHDL code. I will show you. Then it's like use case, domain application. Verilog is like commonly used in maximum industrial application, industrial designs and all. Verilog is very popular, like for ASIC also we use, even for FPG also we use, but majorly maximum like 95% ASICs or Verilog only, I can say like that. Means domain application is Verilog is way more popular when compared to VHDL, and VHDL is like, VHDL is mainly used in like military applications, aerospace applications, as I said. And let us just see the example now. See, this is this is the code for AND gate in Verilog, and the extension is file .v for Verilog, and for VHDL is .vhd. Okay, so this is the basic structure. Means we have not taken any very big code, and you need not to worry about this code and all. We will be going to write so many codes so that you will be very comfortable with hands-on and all. Now you just observe what this contains. This is a code for synthesizing AND gate. Only AND gate. We have two inputs A and B, and we have an output Y. Module and end module is required. This module is required for synthesizing. And then AND gate is the name of the module, and then we have to include this port list. Whichever it is input, we list as input, and whichever is output, we list as output. And we name the ports. And then we are doing assignments that we will see later. Don't worry about this. What we are doing is, we are just doing Y is equal to A and B. This is how the AND gate is. You might be knowing this symbol. This is ampersand and used for AND gate. End module, and we are ending with end module. Like how we do open and end in C, like open curly braces and close curly braces, like that only we are using end, begin and end in Verilog. So we are ending with end module. This is what Verilog code for AND gate looks like. And yes, our VHDL is here, and this is how this code looks like. These two lines are mandatory. You have to use library, because VHDL is a proper fully IEEE standardized, so you must use this library IEEE, and you have to mention which standard logic you are using, like how we use import some package dot star, like that we use, like that only we have to use dot all here, this standard, and from this standard we are using everything. Then we have to use entity. Entity is a keyword here, and then AND gate is your name of the entity, or name of the, means whatever the program you are writing, for that you are giving a name. You have to write, as I said to you, it looks like English only, and you have to give the port names. And here we just use input and output, but here you have to use in standard logic, in standard logic, out standard logic, like that you have to use. These are all keywords. Oh. And then you have to use end entity, like how we use end module here, like that. But next, this is how you are just declaring the port. Means we are at this level, okay. I'll take some another color. I'll take green. Okay, we are still at this level. Okay, now we are entering into actual logic. What we wrote here, assign Y is equal to A and B. What we are writing here, we are assigning Y with A. See, we should not use ampersand here. We have to use proper A and D and spelling. So we have to write this architecture behavioral of AND gate is, we have like structural, we have data flow, we have like that. So many types of modeling we have, and behavioral is one of the types of the modeling, and this is the high level modeling. And here we are assigning Y. This is the logic, and this is the line which synthesizes your AND gate. For that we are writing this much here, and we have to end the architecture. Means entity means you are declaring the port, and architecture means you are defining your design, or you are writing your logic which your design works. This is our Verilog. See, which is simple, you just decide. This is what it is, means because VHDL is strongly typed, everything. If you see this, you will understand what it is. You need not to scratch your head about what is this and all. No, this is strongly typed like you speak. See, I'll just give you an example. In Verilog, how you will do when we are writing something, we will be like 3 down to 0. We read like that, but we write like this 3 and we use some colon and we write 0. You know what we will do in VHDL? We write 3 sorry I'm writing in mouse, 3 down to 0, like that we have to write fully in VHDL. Whatever we are writing this much in Verilog, we are just mentioning 3 and colon and 0, we have to write full in English, 3 down to 0, like that in VHDL. That is the difference. That is what it is, typing structure. Means this is weakly typed, we just have to mention something, but here we have to write each and everything. It is like proper English story you are writing in terms of design. That is what your VHDL is. So this we saw Verilog versus VHDL. If time permits, we will even see VHDL also. Means I have never written big designs in VHDL. Yes, still FSMs I have written in VHDL, till sequence detector and FSM, that and all I have written the code. And yes, I can't say I'm super good at VHDL, yes, but I can say I'm good at VHDL. Yes, we will write VHDL codes also if time permits, and you will definitely, it will be super fun, you will enjoy a lot. But before that we will learn Verilog, and you can start comparing Verilog and VHDL, and it will be really very fun. I can guarantee you that. So let us see now how we are going to execute the Verilog code. Means we have online simulators. I'm not able to see where this point is. Yes, I'll take laser. We have online compilers such as we have JDoodle website, we have tutorials point website, we have EDA playground, we have CoderPad. The difference is EDA playground takes Verilog and system Verilog. If you miss any Verilog if you miss any Verilog syntax, if you just switch to system Verilog syntax, it happens with us because I'll be writing code in like system Verilog constructs only, and very less we use Verilog constructs. So sometimes even if you switch to, sometimes I miss and I switch to system Verilog, but still in EDA playground it will not show error because like it is Verilog bar system Verilog if you see in that website. But in JDoodle or tutorials point or CoderPad, it is properly Verilog, and if you just use any other constructs rather than Verilog, it will throw you an error. That is for sure. So we will not be using EDA playground because we should be very much comfortable with the Verilog syntaxes only. So what we do, we use let us use like alternatively, one class we use JDoodle, one class we use tutorials point, one class CoderPad, like that. You should be comfortable with everything, like that we can do. And offline simulators, we can use ModelSim, QuestaSim and Vivado. Vivado is freely available, free version is there, whereas ModelSim and QuestaSim, I think for ModelSim free version is there, but QuestaSim it might not be there. So we shall rely on online compilers, and then when we are moving towards some major projects, at that time we can use the offline simulators, and we will see what offline simulators we can rely on. So this is how we execute this means whatever the Verilog code we are going to write in future. And yes, from our next session we will be starting officially we will be starting Verilog. That is, we will start with means we just saw the overview. Now I am not going or I don't want to go in depth into like what is Verilog, when Verilog started. What is Verilog, we know already, it is a HDL. and I don't want to get into depth into like when Verilog started, in which 1980 what happened, 1990 what happened, 2005 what happened. No, I don't want to get into all those things. If you are so, or if you are very much interested in knowing the history of Verilog and all, yes, obviously you can read from your side. But what I am focusing will be like, initially we will start with data types. Before that we will see Verilog structure, like how the program structure, we just see some example, and later on from that we will start with the data types, basic data types we will start. And once we are done with data types and how the design structure looks or the test bench structure looks, directly we can head with the designs. Means we design with digital electronics, we will see that design, and then we will just transform the same to the code level, and we will simulate and synthesize it, and we will see how it works. That is how it will be going. Like if you have any concerns or any ideas like this is not comfortable with us, you have to do in some other way like that, if you think like that, you can just put in the comment box, so that I will go through it and see. Ultimately the thing is, you should understand what I'm going to convey. That is my intention. Is if I'm going too fast, or if I'm going too slow, or if you need anything else, you can just put in the comment box, so that I can include it, or if I have to improve the way I explain, that also I will do. Once, as I said, the thing is, you should understand and you should be able to code. Ultimately you are the one who is the learner, and it should be appealable to you, like how the course looks or how the course goes. So this is for today's session. We shall meet in the next session with Verilog. Introduction we did today is Verilog data types, and like how Verilog looks, and we shall see everything in starting from our next session. Means directly we will be jumping into Verilog. So this is for today. Thank you so much for being with me, and yes, please like, share this video and subscribe to my channel, so that you will not miss any updates. And yes, thank you, and have a great day.